In this section of the notes, section 9, we're going to be talking about an extremely important distribution, but also quite an unusual distribution. And this distribution is called the normal distribution. I'm not entirely sure why it has that name, but it's called the normal distribution. And we're going to spend the whole of this section looking at the normal distribution and how to work with it. So before we do anything else, let's start with a definition of the normal distribution. So the normal distribution is a continuous distribution. So in order to define it, we're going to need to write down its PDF. So a continuous random variable x has the normal distribution. The normal distribution is also known as the Gaussian distribution after the mathematician Gauss. This we write x twiddles n mu sigma squared. So we've got two parameters here, mu and sigma squared. Mu is called the expectation for reasons you might be able to guess that are coming up later. And sigma squared is called the variance for reasons that you might guess are coming up later. The expectation is sometimes called the mean here as well, although I personally don't really like that. And the PDF is this thing if it has PDF, probability density function. And now we have quite an odd and complicated expression for the probability density function of the normal distribution. It's this. We start with a normalizing constant, which is 1 over root 2 pi sigma squared. That's pi as in 3.1415. Then we've got an exponential, and because there's so much inside the exponential, I'm going to write x rather than e to the, but it's the same thing. And inside the exponential, we've got minus, we've got a fraction, with x minus mu squared on top, and 2 sigma squared on the bottom, and that's for all real x, so positive and negative. And that is quite a funny looking PDF. One special case, which will turn out to be quite important, is the so-called standard normal distribution. And this is the case where mu equals 0 and sigma squared equals 1. So if we set mu equals 0 and sigma squared equals 1, we've got a normal distribution with expectation 0 and variance 1. And so that has PDF. Bit in front is just 1 over 2 pi, and the thing in the exponential there, you can probably see it's just minus z squared over 2. Now you'll notice I've used the letter z here. That's because standard normal distributions are traditionally given the letter z. Also, their PDF, their probability density function, is traditionally given this letter, which is a lowercase Greek phi. So that's just the PDF of the standard normal distribution. We'd normally write f sub z, but for whatever historical reasons, phi has become used for the PDF of the standard normal. And later, the CDF of the standard normal will be very important. So, of course, we know the CDF is what you get if you integrate the PDF. So that's what you get if you integrate the PDF, and that's normally called this letter, which is capital phi. It should be capital phi of z, though. Give me a moment. Capital phi of z is the CDF of the standard normal. I'm just mentioning that now because it has this special letter, capital phi, and we'll use this letter, capital phi, quite a bit later. So I just wanted to know that's the CDF of a standard normal. So, why is the standard normal so useful? Well, the standard normal is used to model lots of things in real life. For example, if you're looking at the measurement error of some kind of scientific measuring device, some measuring instrument, we'd normally model that error as being normally distributed. Hopefully, if your machine is calibrated correctly, the expectation of that will be mu equals 0. But obviously, depending on how precise your machine is, the variance could be big or the variance could be small. Heights of people is well modeled by a normal distribution. Lots of important models of financial markets are based on the fact that the logarithm of certain prices is normally distributed with some appropriate mean and expectation and variance. It's worth just sketching out a picture of what these PDFs look like. There are precise pictures drawn by R in the notes, which will be exactly right. So these are just my kind of sketchy approximations. And so the normal distribution, if we put x on that axis and the PDF, f(x) of x on this, is often known as the bell curve. Now, my personal opinion is that the bell curve doesn't actually really look like a bell, but nonetheless, it's kind of this thing, sometimes called the bell curve. I think it's meant to look like a church bell, but I don't really think it does. But importantly, the center of this curve is at this parameter mu, and the width of the curve tells us what sigma is. You could try and spot the point of inflection, we sometimes call it, where it goes from turning that way to turning that way. I guess is about there. Then that gap there is sigma, the square root of the variance, as is that there. Although you can't really tell on my picture, this is meant to be symmetric about mu. If you look at the more accurate pictures in the notes, you'll see that they really do look symmetric about mu. And so the idea is by changing mu, you take this bell curve and you shift it to the left or the right, because that's changing where this parameter mu goes. So that would shift it to the left or the right. Whereas if you change sigma, that would change how wide or how narrow the bell is. So if you took sigma very small, you'd have a very pointy bell. Sigma very large, you'd have quite a flat bell. Again, you can see more accurate pictures of these in the notes. So I think a reasonable question here is, why is this very odd formula for the PDF of the normal distribution something that's useful to look at? And so the answer to that will really come later in this section where we talk about the central limit theorem. Roughly the idea is that when you've got something that's like the accumulation of lots of small errors or lots of small variations, then you often get something that looks a lot like a normal distribution coming out of it. So for example, a person's height is affected by lots of small things in their genetics and in the environment. And those lots of small things come together to make an effect that is kind of normally distributed. Same with the price of a stock, or the logarithm of the price of a stock. There are lots of small things in the economy that all change the price of the stock a little bit. And so the combined effect of all of those, as we'll show with the central limit theorem, leads to a normal distribution. So throughout this section, we're going to be looking at the properties of this normal distribution, and we're going to be looking at how to perform calculations using the normal distribution.